A black hole is something that you get when you cram a lot of mass in a small area. Usually it happens at the end of a large star's life. It has very strong gravity that nothing can escape it. It can bend parts of anything, even light. They are eternal. No, they are not eternal. They emit Hawking radiation and evaporate. To understand that, we need to understand quantum fields. A quantum field is a set of quantum properties of a particle with assigned value to every point in space. Did you understand? Imagine it as a water body with energy measurement assigned to all points on it. When the water is still, the energy is hovering over zero in terms of quantum field. Here waves are the particles. Just like the waves have a lot of energy or called as concentration of energy, particles are also concentration of energy. But let's be realistic. Look at the water body. It appears to be still, right? But if you look closely, there are ripples which are continuously emerging and merging into the water body. These ripples are virtual particles in quantum field, which means particle and antiparticle pairs appear from the vacuum and annihilate each other, or disappear in that case. Particles which are appearing from the vacuum are concentration of energy, right? But this is conserving the energy because they return the energy back to vacuum by annihilating quickly. Let's represent it as positive and negative wave modes. In normal conditions, these both cancel each other out, or annihilate in that case. But in presence of a black hole, they aren't able to cancel out. But why? Let's take strings for instance, similar to what we have used to represent the wave modes. Here they have a different number of loops. Normally, we have all of them available to us. But if we pinch them, some of the strings are unavailable. Black holes somewhat pinch the wave modes, which means some modes are unavailable. If some are unavailable, they aren't able to cancel out, which means it has turned vacuum into a particle-filled region. But remember, concentrated energy is a particle, which means particles took energy but did not return. This is violating the law, right? Here the particles have only the black hole around it. And we know energy is directly proportional to mass. Hence, the energy is returned to vacuum by the black hole, which means its mass is reduced. This is called as black hole evaporation. And these particles, which are almost certainly photons, are released in the form of Hawking radiation. But the black holes emit Hawking radiation so slowly that what they feed on still makes them grow. No wonder we don't have any experimental evidence for it. But in the far unimaginable future, the universe will cool down enough to allow the black holes to shrink. And in the last moments, it will explode widely into massive particles. No matter what, every black hole's fate is evaporation after all.